We are continuing in Rosen Discrete Mathematics and its Applications, Section 1.7 on Introduction to Proofs. We have learned direct proof method of proving implications P implies Q. We've learned one indirect proof method for proving implications using the contrapositive of P implies Q. We're going to learn another indirect proof method that can apply to implications as well as straightforward propositions called contradiction. We're going to, also known as reductio ad absurdum, meaning that we're going to assume the opposite and prove a falsehood in order to prove the truth of the original statement. So the way it works is we are going to want to prove R, proposition R. We're going to assume the negation of R, and then we're going to derive a contradiction, such as S and not S, or something like that. It'll be a clear contradiction. Once that is accomplished, this contradiction, whatever it is, will be a falsehood. That means we will have taken the negation of R and proven a falsehood. By the contrapositive of that statement, that negation of R implies false, the contrapositive of that is that truth implies R, and therefore R would be true, since truth is always true. Okay, let's take a look at an example. We want to prove that if you pick 22 days from the calendar, at least 4 must fall on the same day of the week. So I want to write this down below as an implication, and then we're going to take the negation of it and show that a falsehood results. So pick 22 days. That means at least 4 will be same weekday. That's what we want to prove. So by contradiction, assume the negation. So that means if we take the negation of an implication, remember that's going to be the hypothesis negated or the consequence. The negation of that will be the hypothesis and the negation of the consequence. So pick 22 days and we're going to assume this, and less than or equal to 3 will be on same weekday. So that's the negation of the proposition we want to prove. Well, what happens when we do that? We're going to, so let's go ahead and build out the solution. So we're going to assume that we pick 22 days and that no more than 3 of them fall on the same day of the week. Well, the problem with that is if no more than 3 fall on the same day of the week, the most we could pick is 21 days. So this implies that we pick 22 days and we pick less than or equal to 21 days. And that is a falsehood. Is the equivalent to a falsehood. So what we do in this case is we write 2 arrows pointing at each other, which states contradiction. And because we've reached a contradiction, that the negation of our original implication implies false, that means truth implies the original implication. All right, I will do another video that lays out how use of contradiction on implications is closely related to proof by contraposition. But contradiction is very powerful at proving other types of propositions. We'll show how we use it for some non-implications next. Proof by contradiction. Here we're going to reach forward into chapter 4 for a concept. And we've talked about this a little bit, but we want to use proof by contradiction to prove that the square root of 2 is irrational. Well, we were going to, so that's the proposition. Prove that square root of 2 is irrational. Well, we want to assume the negation of that. Suppose that it is rational. We want to prove that it's irrational. So we'll suppose that it's rational. All right, we have a definition of rational, that there are integers a and b, such that square root of 2 is the ratio of a to b, where b is non-zero. And then we're going to add a feature to this definition, such that a and b have no common factors. Okay, so that's an addition to the definition. We can always show that if we have a rational number, that it is the ratio of two integers such that they have no common factors. All right, so now we have square root of 2 is equal to a divided by b. They have no common factors. If I square both sides of it, I get 2 is equal to a squared over b squared. Multiply both sides by b squared, I get 2 times b squared is equal to a squared. But notice that a squared is equal to 2 times b squared, and b is an integer. So b squared is an integer. That means that a squared must be even because it's twice an integer. Well, if a squared is even, then a must be even. Now that is something we haven't proven. It's an exercise for you to do, but we've already done something very similar with a squared odd implying a must be odd. So you would proceed similarly to prove this. All right, so if a squared is even, then a must be even. That means a is equal to 2 times some integer c. So let's substitute. And that means we're going to get 2 times b squared is equal to 4 times c squared. Well, now we can divide both sides by 2, and we get b squared is equal to 2 times c squared. But now b can be said to be an even number because it's twice an integer, namely c squared. So b squared is even, and then by this exercise that we are leaving to the student, b must be even as well. But what do we have? We have a is even and b is even, and we do that, but that means they both have a common factor, which contradicts our assumption that they don't have a common factor, which is in the definition of rational. So we can conclude then, since we've reached a contradiction, assuming that square root of 2 is rational, that square root of 2 is actually irrational. All right, we have another proof by contradiction to do, and another preview of chapter 4. We want to prove that an infinite number of primes exist, or that there is no largest prime. And so what we'll do is we'll assume the opposite, that there are a finite number of primes. And if you have a finite number of primes, it must be a largest prime, and we'll call it p sub n. So if I have a largest prime, I can list them all out theoretically from 2 the first prime, 3 all the way up to p sub n. I'm going to create a new number called r, which is the product of all of my primes. I'm going to add 1 to that product. Well, there's 2 things that could be true about r. First of all, we note that none of these primes can divide r, and therefore r is either prime or there is a smaller prime that divides r. So The theorem states that none of these can divide R, this theorem from chapter 4. Therefore, R is either prime, or if it's composite, there's a different prime than the one on this list. The bottom line is that this list is not complete, even though we assumed that it was. We got a contradiction. Therefore, the number of primes is infinite. Okay, one more concept to cover, and that is the proof of the biconditional. And this one follows from one of the earlier identities, that P if and only if Q is the same as P implies Q and Q implies P. So whenever we want to prove a biconditional, we'll just prove two implications. P implies Q and Q implies P. And then we'll have proven the biconditional. Here's an example. If n is an integer, then n is odd if and only if n squared is odd. Well, we've actually already proven that n odd implies n squared is odd on a previous slide. And we've proven by contraposition that n squared odd implies that n is odd. And so we have actually already proven this theorem on previous slides. And so we could say that it is a biconditional statement is true. By the way, if you encounter if and only if in a mathematical phrase, it is sometimes abbreviated IFF. So n is an integer, then n is odd if and only if n squared is odd.